In this part of physics, we are going to talk about problems that occur with lenses. And you're going to take two problems that are real applications of the manufacturing or the natural defects in lenses. And also we're going to study Young's experiment, that is a great experiment to demonstrate that light is moving as a wave. So on the previous video, as we studied that lenses have many applications, and from these applications is we use them for people who have problems in sight. And we said that there are two different problems with sight. We have farsightedness, and also we have what? Nearsightedness. And you said people who suffer from farsightedness, they can see what objects that are far, but they cannot see objects that are what? Close. And the problem is, we said that normal people, usually the images are here formed on a point that is called what? Retina. And this retina, it will be sent as a signal, nerve signal to the mind, and then it can be analyzed what type of image is it. So, but people who have a problem or classified as farsightedness, their problem is the images are formed here behind the retina. So that means no signal is sent to their mind to analyze what images. So that means they can't see it. So in this case, what we need to do, we just give them what? Convex lens. And this convex lens will converge the rays to help their eyes to converge more the lens. So that means here to move the formation of the image, instead of being behind the retina, then it can be on the retina, so they can see, or they can understand what image they see. And we understand that the eye itself, it works as convex lens, so it converges light. It converges what? Light rays. And we understand that nearsightedness people, on the other side, they have problem that the images are formed here in the point before or in front of the retina. So that means now there is no signal sent to their minds to analyze what image they see. So in this case, to solve their problem, we use what? Concave lenses to spread out the rays here. So then when the eye comes as convex lens, it converges them again. So they are converged on the retina, then they are sent to the mind by nerve signals. So we understand that they understand what image they see. Okay, here now, just we need to understand that this convex lens now, when it converge the rays, it converges them to only one point. And this is its job, and this is what is this lens supposed to do. Okay, but now we have problems with the lens itself when it doesn't converge the rays into a specific point. Here, for example, on this example here, as you see, this one now is normal convex lens, even if it is half lens, but it works the same like what? Like a complete lens. Even it's not like this here, but it makes the same job. It makes what? The same job. Okay, for this one now here, as you see, all the rays are converged into a specific point here called what? Focal. So that means this one now is a lens that is correct lens, and it makes its job perfectly. But what happens now when there is a problem in manufacturing, or the length of the lens is wider than expected? When the length is wider than expected, what happens then? The rays now, as you see, are not converged into just one point. So that means it converged into too many points here. So that means in this case, if a person suffers this problem, which is called spherical aberration. So this one is called the spherical aberration. People who have problems were classified that they have spherical problems in their eyes. That means the lens of their eyes is not working to give a real signal about how the real image is. So how are they going to see the images then, real images? This is now here example here. As you see, this is now how the real picture is. And this is how people who have a problem with a spherical aberration, how the image they see it. What's the problem here? The problem is their eyes, it does not converge the rays of the images perfectly to one single point. They are converged into many points. Okay, this is now one problem of the lenses, whether it is the lens of the eye or the lens of glasses. Okay, another problem here is called chromatic aberration. And what is chromatic aberration? Chromatic aberration on the lens, it happens due to that the light here now that is coming to the lens is dispersed into what? Into many points instead of one point. But it dispersed as colors. So the colors here now, instead of one color moving ray to move here, you're gonna see that it got dispersed, and the problem here is color dispersion. So that means it's dispersed into many points. So people, they see lights or colors on the picture. How? This is now an example. So this is how normal people see the picture here. And the problem, people who have problem with chromatic aberration, they see this picture now like when there is what colors here. You see it here. They see like there is what colors on the picture. And this is the problem of dispersion of light on the lenses. So we understand now the problems that come as a result of lenses or that lenses have. And now we go to next point. We'll go now into Young's experiment. What is Young's experiment and what is it used? So this is, as you see, this is Young's experiment slit. What is Young's experiment slit? Okay, this experiment now, when the rays of light is coming into one slit here, as you see it, a slit, one slit here. These rays now will be converted like this is now, like if it is a new source of light. So that means they'll move, as you see, on this way, like if this point now is the source of the light itself. So that means now, instead of moving now, the light moving gets in a straight line and to this point only, as you see, no, it is moving in waves in all the directions around this slit. And this is now a proof that the light is moving as waves, not as particles. Because since if it is as particles, it will move directly and it will stop what? Here only. From this slit, it will make just here. But now, as you see, it moves as waves in all the directions. Okay, now if we make another here barrier with two slits, and now we have what here, as you see, two slits. This is now one slit, and this is what? One slit. What will we see? We'll see now these ones now they'll work like two sources of light, and the light will move like waves. And these waves now, as you see, at these points, as you see, what happens? They overlap with each other. When they overlap with each other, this is, we call it interference. At interference, we have destructive and we have what? Constructive. Now, when they interfere on this point now, this interference, we call it what? Constructive. And this one now, they give us here light. This is now screen. This is screen, they give us what? Light here. So this is bright band and this is what? Dark band. So that means when the interference is constructive, they give us what? Here, bright band as light. And when it is here in this place, it means destructive. So destructive, they give us like dark band or fringe. So we understand now light is moving as wave here, and we understand that the light waves overlap each other, interfere with each other, and this interference can be constructive and can be what? Destructive. Okay, now based on this experiment now, Young's produced or created what? A formula. What is this formula here? He said the wavelength of this light, its wavelength, it equals x times d over L. Okay, what is x and what is d? The distance between these two slits is called what? D. The distance between this hole and this hole is called what? D. And the distance between this place and this and the screen, which is the two slits bar and the screen, is called what? L. And now this one we call it primary or main or central brand. This one now we call it what? Central brand or central bright brand. Sorry. And the distance between this line here and the screen, this distance, we call it what? L. So this one is called L. And now it is X. So this one here, which is the middle bright band, we call it what? Central bright band or fringe. And the second one here, we call it the first bright band. So we have here central, and we have what here? First. The distance between the central band and also the first bright band, so this distance now is called what? X. So the distance here is called what? X. So you understand now what is X, we understand what is L, and you understand what is D. So now just we apply what? The formula. We apply the formula, which is now wavelength of the light equals X, which is the distance between the central bright band and the first bright band, and times the distance, which is the distance between the two slits, over the distance between the slits and the screen. Okay, now we solve a question based on that. Okay, based on Young's experiment, we solve what? This question. In Young's experiment, students used laser light with wavelength 600 nanometer. If the students put the screen 1 meter away from the two slits, they find the first bright band 60 millimeter from the central band. Okay, as we know, that means these ones now are the two slits here. And these two slits, they sent what? Then into the screen. The waves into what? The screen. And the screen we have here central band. And then we have here what? The first band. And the distance between them is called what here? Is called X. And the distance from here to here is called what? L. And the distance between these two slits is called what? D. And what's the formula now? The formula is the wavelength equals X times D over L. Okay, the wavelength now is given for us. So this one now is the wavelength. If the students stood, let me see, 1 meter away from the two slits, so that means this is L now. What also is given here, they find the first bright band 60 millimeter from the central. So that means this one is what? The X. What they are asking about, the distance between the two slits, which is what? D. And I should make sure that before I start solving, I should make sure that all the units have to be in meter, in SI unit, which is what? Meter. So nanometer here, I'm gonna multiply it 600 times 10 to the power of what? Of -9, to change it from nanometer into meter. And here now, 60 millimeter, I'm gonna multiply the 60 times 10 to the power of -3 to change it from millimeter into what? Meter. Then the next unit, it is also already in meter. Now we go to solve. Now I put just each one in its place. So this one I put it here, and this number I put it as x here. Then I solve when the L is 1, I put it here. So that means now wavelength, as you see, it's going to be 600 times 10 to the power of -9 equals x times d, which is 60 times 10 to the power of -3 times the distance, which is d, over what? Over L, that is 1. Now, just to solve to find d, we divide both sides by 60 times 10 to the power of -3, and here divide by 60 times 10 to the power of -3. And here, as you see, this one will go by this one here. So d equals what? Here, 600 over 60 will become 10. Now, 10 to the power of -9 over 10 to the power of -3, 10 to the power of -3 will go up as plus. So that means it's going to be -9 plus 3, it's going to be -6. So what is left is 10 times 10 to the power of -6. 10, it means power 1. So when we multiply them, we add the powers. So it's going to be 10 power what? -5. This is the distance, and the unit is in meter. So you got to choose 1 times 10 to the power of -5 meter as the answer.